Good morning, everyone. And once again, we are back with one important talk today. रीजनल साइंस सेंटर भोपाल जो है आप सब जानते हैं नेशनल काउंसिल ऑफ साइंस म्यूजियम्स की एक यूनिट है मध्य प्रदेश भोपाल में. Under our council, we have 26 science center in different parts of our country. And today in Bhopal, we are very fortunate and we are also honored to have Professor Ashoke Sen. Before inviting him on the dais, I'll introduce him so that you can understand. As you all know, the science centers are a very critical part of our society. They are becoming more important catalysts to take science to the people through various modes of communication, engagement, participatory exhibits. We have number of galleries, and there are many, many activities. Year long, we have been organizing a lot of engaging workshop, popular science talks, and interactions, podcasts, panel discussions. All of them are having common goal, taking science to millions. Science communication, popularization of science, and very important, trying to create a critical thinking and scientific temper. On that note, our council has very much engaged not only with the help of science centers under this umbrella, and under the single umbrella, NCSM is the largest known body across the planet. And today, when we are going to introduce Professor Sen, it is really privilege and honor for me and for my science center and on behalf of our council also, because perhaps, as he said, that this is his first talk in NCSM's Science Center. That's really great and honor, sir, for accepting our request through ICER, ICTS, which is supported by, this Asian school is supported by Murthy Trust. We will have his interaction, post interaction, we will request him to engage with all of you, and we'll have very small Q&A session. And post that, you are free to discuss even when he's just leaving the dais, subject to his availability and permission. So distinguished guests, respected faculty members, students, friends of science, our live audience also, from wherever you are watching this live feed, will be honored. If you have any questions, please type in live chat. Our team, I'll request my colleague, Rajesh, Swapnil, and also Vivek and others, if they have access of this live chat questions, we will take those questions at the end. It is my pleasure and honor, I must say, to welcome you all to the Regional Science Center Bhopal for today's special popular science lecture. Regional Science Center Bhopal has just completed, sir, on this 12th of January, 31 years in the state of Madhya Pradesh under our council. It is a part of National Council of Science Museums, non-profit scientific organization functioning under the aegis of Ministry of Culture, Government of India. We are honored to host a scientist whose work has profoundly shaped modern thinking about the fundamental nature of the universe. It is a privilege to introduce Professor Sen, one of the most distinguished theoretical physicists on this planet, Earth, Marble Blue or Blue Planet. Professor Sen is internationally renowned for his pioneering contribution to string theory and quantum gravity, addressing some of the deepest questions in physics about the fundamental constituents of matter, which I say nature, the unification of forces, and the relationship between gravity and quantum mechanics. A faculty member at the International Center for Theoretical Sciences, TIFR Bangalore. At present, he's working over there, but he has a very long span of career, worked many, many institutions, including very famous HRI Allahabad. His quality of lifetime also is spent over there. Professor Sen has received some of the highest honors in science, including Padma Bhushan, the Dirac Medal, the Fundamental Physics Prize. Very inspiring, reflecting the depth and global impact of his work. He is also widely admired for his clarity of thought and his ability to communicate complex ideas with insights and inspiration for students and researchers across the planet. Today's lecture, Search for a Unified Theory, will take us into the heart of modern theoretical physics and the continuity scientific quest to understand the universe as a coherent whole. This lecture is being organized as a part of the 20th Asian Winter School on Strings, Particles and Cosmology, hosted by ICER Bhopal in collaboration with ICS TIFR. with support from Murthy Trust. On behalf of Regional Science Center Bhopal, our council, it is our great honor and privilege to welcome Professor Sen. Let us give a round of applause for Professor Sen. Sir, please join us on the dais. Thank you.
Now I request our head of the Regional Science Center and from all of us a token of love to Sri Ashoke Sen sir, जो हमारी परंपरा है एक पॉटेड प्लांट देके प्रकृति को ध्यान में रखते हुए. Thank you so much sir.
Thank you, Rajesh. And can I have another mic?
I can start.
Yeah, to start.
Thank you very much. Okay, so it's really a great honor for me to come here and give this talk. And thank you all for coming so early in the morning. So today my talk is going to be on search for unified theory. Time. 11:06. Okay. So this is the title of the talk. So let me begin by describing what this talk is going to be about. We probably all know that one of the goals of science is to discover the fundamental laws of nature. And in particular, we may want to know what are the basic constituents of matter, what is it that all of us are made of, and what are the laws that govern their properties. And the goal of this talk will be to describe what is known, what is not known, and also, most importantly, how we attempt to know what is not known. So let me begin by describing the modern understanding of the building blocks of matter. Okay, this is something that is known to us, and I'll try to describe what is known. So just as an example, let's start with water. Okay, what are the constituents of water? Now the crudest building blocks of water are the molecules of water, which we call H2O. But as the name suggests, okay, it's not really a fundamental object. Okay, it's made of more elementary building blocks. Okay, in particular, each water molecule is made of 2 hydrogen atoms and 1 oxygen atom. Okay, this is what I have shown here. So then one can ask, are the hydrogen and oxygen atoms themselves elementary? And perhaps all of you already know the answer that that is also not the case. Because once we probe deeper into the atoms, we find further structure. In particular, each atom is made of a central nucleus and a set of electrons around it. So the hydrogen atom, for example, has a hydrogen nucleus and is 1 electron surrounding it. The oxygen atom, on the other hand, has an oxygen nucleus and 8 electrons surrounding it. Okay, so these are much smaller particles than the atoms themselves. We can probe deeper. Okay, we can ask, are the electrons and the nucleus, are they fundamental objects? Now it turns out that when you probe deeper into the electron, we do not find any structure. Okay. So we say that according to our present knowledge, electrons are indivisible. Okay, we call them elementary particles. Okay. But this is not the case for the nucleus. Okay, as we probe the nucleus, we find even smaller particles that are hiding inside the nucleus. So in particular, we find that each of the nucleus is made of certain number of protons, okay, which are smaller particles, and certain number of neutrons. Okay. So for example, the hydrogen nucleus is made of a single proton. Oxygen nucleus, on the other hand, has 8 protons and 8 neutrons, okay, which is what you see here. Now why stop here? We can probe even deeper into the protons and neutrons. Okay. And indeed we find further substructure. Okay. We find that protons and neutrons are made of even smaller particles which have come to be known as quarks. Okay. So for example, inside the proton we find two quarks of U type and one quark of D type. These are also sometimes called the up quark and the down quark. Okay, but those are just the names of these particles. And neutron on the other hand is made of two down quark and one up quark. Okay, so even protons and neutrons are not quite the elementary particles. So far we have not found any further structure inside the quarks. So from this viewpoint we can say that according to our current knowledge, quarks and electrons are the elementary constituents of matter. But it turns out that these are not the only elementary particles that we have in nature. Because if we collide two very energetic elementary particles, say we take two electrons, okay, accelerate them to very high energy and collide them, okay, we find that as a result of the collision they produce many more particles, okay, and that can happen because of this famous relation due to Einstein, which says that energy can be converted to mass. Okay, so you throw in electrons at very very high energy and they come out as many elementary particles with heavier elementary particles with various masses. Okay. So this way you have come to know about many elementary particles that exist in nature, and I'll give you the full list, okay, at least full list of known elementary particles later in this talk. If we really want to understand the properties of matter, then it's not just enough to know what kind of elementary particles are there inside each object. Okay. We also need to know their properties, okay, in particular what kind of forces those elementary particles exert on each other, okay, because only then we can hope to explain the behavior of matter that is made out of those elementary particles. And according to our current knowledge, there are four major kinds of forces that are known to us. And here I'll give a list of those four forces. Probably most of it is also familiar to you. We have the gravitational force. Gravitational force is the force that, for example, is responsible for Earth's gravity, or the motion of planets around the sun. Second, we have electromagnetic force. Electromagnetic force is responsible for the force of a magnet or the binding of electrons to nucleus in an atom and so on. In the absence of electromagnetic force, for example, the atoms will not form even if there are electrons and nucleus, because there is no force that binds them together. Okay, so it's important to know that there is electromagnetic force that operates between the electron and the nucleus. So going ahead, one finds that there are also forces which are called the strong forces, okay, and weak forces. The strong force, for example, is responsible for binding the protons and neutrons inside a nucleus, okay, or binding of quarks inside protons and neutrons. Okay, without strong force, the protons and neutrons will not be formed out of quarks. And finally, we have the weak force, okay, which is not really responsible for any binding that we see in nature. But without weak force, for example, we cannot explain many kinds of radioactive decays that we see in nature. Okay, so weak force is also necessary for explaining some of the natural phenomena that we see. Because of these forces and the complicated nature of these forces, they give rise to complicated interaction between the elementary particles. Okay. And so one may ask that how do you know that there are these kinds of forces? Okay, how can we experimentally test their properties? Okay. And the answer is indeed yes. The way we measure these forces, okay, is by studying how the elementary particles scatter off each other. Okay. So a typical experiment involving these elementary particles, okay, involve taking, say, two of these particles, accelerate them to very high energy, okay, almost the speed of light, and then make them collide. Okay. So you take two very highly energetic elementary particles, and when you collide them, okay, typically again because of the conversion of energy to mass, what comes out is a bunch of other elementary particles. Okay. And by examining the outcome of this collision and many collisions, okay, we can work backwards and we can actually figure out what kind of forces operate between these elementary particles. Okay. And that's how we know the properties of all these different kinds of forces that we have seen in nature. Okay. Except the gravitational force, which I'll be mentioning in a few minutes. Turns out that even though there are these four kinds of forces that we have discovered, the effect of gravitational force between elementary particles is negligible compared to the other forces that we see. And we can see this by a reasonably simple calculation. So what we have to do is to compare the electrostatic force between two protons and the gravitational force between two protons. Okay, and just for to simplify the analysis, we can just take them to be at rest, and we can ask, how does the gravitational force compare with the electrostatic force? And here is a simple calculation. The gravitational force between two protons is given by the Newton's law of gravity, which involves the Newton's gravitational constant, the square of the mass of the proton, because we are considering two protons. And then there is this inverse square law, which tells us that the force falls off as 1 over r square, where r is the distance between the protons. Similarly, the electrostatic force in CGS units is given by this formula over here. This is called the Coulomb's law of electrostatics. And now we see that this ratio involves only the fundamental constants, because since both are inverse square, you don't have any dependence on r anymore. And when you put in the values of these fundamental constants, g for example is given here, the mass of the proton is given here, and the charge of the proton is given here. When you put all those values in this formula, we find that the ratio is extremely tiny, okay, 10 to the minus 36. So this basically means that the ratio of the gravitational force to electrostatic force is 10 to the 36th fraction of 1. Okay, so that's a really tiny number. Okay, and there is no way that in current experiments involving elementary particles we can ever see the gravitational force between these particles. Nevertheless, we know that the gravitational force is present among the elementary particles, because after all, Earth and Sun are both made of elementary particles, and they do have gravitational force operating between them. And so that basically shows that even though we cannot measure them directly involving elementary particle experiments, they must be present in nature, okay, and they must also be acting between the elementary particles. So far this has been very descriptive, okay, but if we really want to understand the properties of elementary particles and understand the laws of nature, what we need to develop is a theory of elementary particles. Now, what is a theory? A theory essentially is a consistent mathematical framework that describes the elementary particles and the forces. The example of a theory is Newton's law, right? Newton's laws probably many of you are familiar with, which equates force to mass times acceleration. And this basically says that if we know the force acting on a particle and if you know the mass of the particle, you can calculate its acceleration, and once you have calculated the acceleration, you can predict subsequent motion of the particle. So this is the example of a theory. And the goal of a theory, as I said, is to make prediction for the results of any experiments that involves the elementary particles. Turns out that the theory of elementary particles is more complicated than just simple Newton's laws. Okay. And there is a good reason for why this is more complicated than just Newton's laws. And that is the following. Okay. That while developing a theory of elementary particles, okay, we have to remember two important points. The first point is that in typical experiments that we do involving the elementary particles, okay, they move very fast. Okay. They move at a speed that is close to the speed of light. Okay. In fact, many of the experiments that we perform today, okay, the elementary particles, okay, come say 99.999% of the speed of light. right? So it's really close to the speed of light. And at that speed, we cannot apply standard Newton's laws for classical physics. Okay, we need to use what is called the special theory of relativity. Okay, and this is the theory that was developed by Einstein many years ago. Second reason why the theory of elementary particles is complicated is because they are very small. They are tiny objects, and because they are so tiny, if you want to make any measurement on the elementary particles, okay, you have to shine light, okay, or you have to do something to the elementary particles, and that disturbs a particle. Okay, so this puts certain limitations on how well you can study elementary particles, and these limitations are encoded in what is called quantum mechanics. Okay, so we need this new language, okay, of quantum mechanics to describe the elementary particles because they are so tiny. Okay, and this theory again was developed more than 100 years ago by various people, some of whose names I have mentioned here. Turns out that we are lucky and we do have such a theory which describes the elementary particles. Okay, and this theory has been so successful that it has come to be known as the standard model. Okay, and as I have already said, this theory is based on the principles of quantum mechanics and special theory of relativity. Okay, and because you have a theory, okay, in principle this theory can be used to calculate the result of any experiment that you use to perform involving elementary particles. Okay, in particular, if you take two electrons, accelerate them to very high energy and collide them, okay, you can ask what is the probability that you will get two electrons out at 30-degree angle, okay, from the initial motion. You can make a precise prediction of what that probability is based on this standard model. Okay, you can also ask what is the probability that you collide two electrons at very high energy and you get back some other elementary particles. Okay, even those probabilities can be calculated based on the standard model. Okay, and indeed, so far the standard model has been extremely successful in explaining almost all observed experimental data. Okay, I said almost all because there are some exceptions and that I'll mention in a few minutes. Okay, but one of the main shortcomings of the standard model, okay, is that it does not include gravity. Okay, nevertheless, the reason that it has been so successful, okay, is because, as I already told you, the gravitational force between elementary particles is so tiny that in no current experiment, okay, we can see actually gravitational force between the elementary particles. Okay, it's very small. Okay, so even though standard model does not explain or include gravity, okay, it is nevertheless very successful in explaining the property, the various experiments that we perform involving the elementary particles. So here I have given a list of elementary particles, okay, that are supposed to exist according to the standard model. Okay, so here you see our familiar quarks that I already mentioned, okay, the U and the D quark. Okay, the new feature that you see here, okay, is that there is not one kind of U quark. There are in fact three kinds of U quark, which are denoted here by U1, U2 and U3. Okay, there are similarly three kinds of D quark, okay, which is here, and then there are various other kinds of quark, 12 more, right? This is called the C quark or the charm quark, S quark, and top and bottom quark, right? So there are all these quarks that are there as part of the standard model. Then there is another kind of elementary particle which are called leptons. Okay, you see the familiar electron over here, okay, but there are 5 other particles that you see in this list, right? This is called the electron neutrino, this is muon neutrino, and tau neutrino. And what I have not displayed in this list is that for each of these quarks and leptons, they also have their antiparticles. Okay, so for example, for the up quark there is an anti-up quark. Okay, for the electron there is an anti-electron, which is also sometimes called the positron. Okay, and these have opposite electric charge compared to the electron. Then there is a third kind of elementary particles which I have called mediators. Okay, these mediators are the ones that are responsible for the forces that operate between the elementary particles. Okay, for example, there are 8 elementary particles called gluons, These are the ones which are responsible for strong interaction or the strong force that operate between the quarks. There is this elementary particle called the photon. Okay, this is responsible for the electromagnetic force that operate between the elementary particles. Okay, and then there are these other three particles, W plus, W minus, and Z. These are responsible for weak interaction between the elementary particles. And finally, there is the Higgs particle, okay, which stands by itself. Okay, and this also is part of the standard model. Okay. The other feature is that unlike quarks and leptons, which have their antiparticles, these particles don't have any antiparticles. They are in fact their own antiparticles. Okay, so this is the all the particles that you have in the standard model. Okay. And indeed, by now we have discovered all the particles that are listed in this table. Okay. Even though when standard model was first formulated, many of these particles are missing from the list. Okay. So theory predicted, for example, that the Higgs particle must exist. Okay. And the theory had to wait for about 40 years before the Higgs particle was actually discovered in experiments. Okay. Similarly, various other particles like that P quark, for example, was predicted to exist by the standard model, and only later it was discovered in experiments. Even though the standard model has been very successful, we know that it cannot be the final story, and there are some various reasons for why it cannot be the final story. First of all, it turns out that there are some experiments which do not agree with the prediction of the standard model. Okay, so this is a clear indication that the standard model cannot be the final story. Okay. And here is an example. Okay. According to the standard model, the neutrinos have no mass. Okay, we saw the three neutrinos in this list: the electron neutrino, the mu neutrino, and the tau neutrino. Okay. These standard model says that these particles must have no mass at all. Okay, just like the photon, which also has no mass. But experiments show that the neutrinos have small but non-zero mass. Okay, in fact, when the standard model was first formulated, okay, people did think that neutrinos have no mass. Okay, because they really have very tiny mass, but only much later it was discovered that the neutrinos do have some mass. But these discrepancies that we see here, okay, in essence can be easily explained by a minor modification of the standard model. Okay, so it's true that the theory as written down, okay, which is now called standard model, doesn't quite work. Okay, but there are small modifications that we can do, okay, that actually makes the theory work. And this doesn't require giving up any of the basic principles which I mentioned, namely special relativity and quantum mechanics. However, there is a more serious reason why standard model is not complete. Okay. And that reason is that it does not contain one important force that we observe in nature, namely the gravitational force. Now, as I have emphasized several times, in all present experiments, gravitational force between elementary particles is extremely tiny and it's beyond measurement. Okay. Nevertheless, if you are trying to formulate a complete theory of nature, okay, then it must explain all forces, however small they may be. Okay. Because after all, we know that Earth and Sun gravitate, okay, and it must follow from some elementary properties of the elementary particles. Okay. So even though elementary particles, we don't see the elementary particles gravitate because the gravitational force is very small. Okay. We know that they must gravitate because otherwise Earth and Sun will not have gravitational force. Okay. And the question is, what explains the gravitational force between these elementary particles, even though they are very tiny? So this leads us to the question, is it possible to modify the standard model so as to include gravity? Okay. And for this, let's remind ourselves again that the standard model is based on these two principles, special theory of relativity and quantum mechanics. Okay. So if you are to make gravity included in the theory, we have to first make the theory of gravity consistent with these principles, special theory of relativity and quantum mechanics. The first step, which is to make gravity consistent with special relativity, okay, This in fact was carried out by Einstein in 1915, more than 100 years ago, and this is what we call today the general theory of relativity. However, the bottleneck is the second step, and that is to make gravity consistent with quantum mechanics, and this turns out to be an extremely difficult subject, and I'll try to explain what the difficulties are. The main difficulty comes from the fact that in Einstein's theory, the gravitational force between two objects is proportional to the energies of the objects. Now you are probably familiar with the fact that the gravitational force is proportional to the mass. The more massive the object, the more is the gravitational force. But here we see that the gravitational force is proportional to energy, and the reason that happens is because of this famous relation again by Einstein, which relates the energy to the effective mass that the particle carries. So this relation basically tells us that the energy in fact behaves as mass, and the more energetic the particle is, the stronger is the gravitational force. Okay, and that's what I've said here. Higher the energy of the object, stronger the gravitational force. And due to this increase in force with energy, it turns out that the answers to sensible questions turn out to be infinite. Okay, which is clearly not a sensible answer. For example, I told you earlier that if we collide two electrons, then standard model tells you how to calculate the probability that they'll emerge at a 30-degree angle from the initial motion. If we try to answer this question after including the effect of gravitational force, we find that the answer to that probability is infinite. Clearly that's not a sensible answer because the probability cannot be infinite. Right? It should be some finite number. So this is the sense in which gravity is hard to combine with quantum mechanics. Okay, because of this growth of gravitational force with energy. So this is as much as we know today. And whatever I have told you so far is reasonably well understood. What I am going to tell you now is exploring what is not known. Okay, so whatever I am telling you from now onwards, okay, you have to be suspicious of what I am telling you. Okay, and eventually maybe one of you will decide whether it's correct or not. The question, the central question that you want to address is how can we get a sensible quantum theory of gravity? String theory is the subject that I work on. This provides a possible way out of this problem. Although as I have said, the story is in no way complete. What is more, it turns out that the string theory also provides a possible way of combining a theory of gravity with the theory of elementary particles. Okay, and this is in the rest of the talk. I'll try to describe what string theory is about and what stage the theory is at present. Okay. But again, I should caution you that this is still work in progress. Okay. And while lot of progress has been made, lot of progress is still to be made. So the basic idea in string theory in fact is quite simple. Okay. It says that the different elementary particles are not really particles, neither are they different. They are just different states, vibrational states of a string. So string, here I have denoted for simplicity a string with no ends. This is called a closed string. So if you have a string, if you stretch it and let it go, it will vibrate. And the basic idea in string theory is that these different vibrational states, okay, some may vibrate in symmetric fashion, okay, as you see here, some may vibrate in a different mode. There's different vibrational states, okay, and some may vibrate a lot, some may vibrate a little bit. Okay. These different vibrational states of the string manifest themselves as what we call different elementary particles. Now this sounds very strange because if this is really the case, why haven't we seen this? Okay, because I told you that electrons, for example, we have explored electrons, okay, and it looks like really particles. You have not found any structure of the electron. Okay. If electron was really a string, shouldn't we have seen this in experiment? The answer to this is provided within string theory itself. One can estimate what the typical size of a string is. And one finds that this size is in fact very, very small. Okay. It's of the order of 10 to the minus 33 centimeter. Okay. Just to give an idea, okay, at present we have only been able to explore a distance scale of the order of 10 to the minus 17 centimeter. Okay. So clearly the size of the string is much smaller than any distance scale that we can probe today. Okay. So even if string theory was right, okay, in all present experiments it will look like a particle. Now since we have emphasized so much on the special theory of relativity, that is a theory that is needed for describing fast moving particles or fast moving objects, okay, and quantum mechanics, the theory that is needed for describing small objects, okay, we have to also use the same principles to formulate string theory. Okay. So you need to formulate a theory of strings that is consistent with these principles. And here one finds a first surprise, okay, that just as a consequence of these two requirements, strings automatically exert gravitational force. Okay. In particular, if you recall the list of elementary particles that I showed you, in this list, okay, among the mediators, you see there is the mediator of strong force, mediator of electromagnetic force, and the mediators of weak force. Okay. But there is no mediator of gravitational force, okay, and that is because standard model does not include gravity. Okay. But in string theory, on the other hand, just by demanding these two, okay, we automatically get a particular state of the string that is a mediator of the gravitational force. Okay. So in a sense, string theory was not designed as a theory of gravity. Okay. Gravity somehow fell out of string theory. Okay. And I told you earlier that it's extremely difficult to try to make gravity consistent with quantum mechanics and special relativity. Okay. What we see in string theory is that once we have strings and you combine that with the requirement of special theory of relativity and quantum mechanics, it's not possible to get rid of gravity. Right? Gravity is automatically an integral part of the theory. Okay. So that's the sense, okay, in which gravity is included in string theory, and that's the reason why people are excited about string theory, that it may ultimately provide a theory of nature. We may ask what happened to these infinities that we encountered earlier. Gravitational force still grows with energy. But what happens is that by smearing the energy over the string, okay, instead of the energy concentrated at one point, it's smeared over the string. Okay, it turns out that that is enough to tame the effect of the growth. Okay, even though the gravitational force, net gravitational force grows with energy, okay, when you collide two strings at very high energy, okay, it only intersects at in a small region, okay, one string and another string, and effective gravitational force decreases that short distance. Okay. And this is the reason why the answers to sensible questions now turn out to be finite instead of infinite. The price you pay, however, okay, is that string theory is very, very tightly constrained. Okay. In fact, there is a unique way of writing string theory. Okay. There is no, the laws of string theory are given once and for all. Okay. And unlike the standard model, which you can tweak, right, just as I said, that you can accommodate neutrino masses into the standard model by simply making a small change in the theory. Okay. That kind of small change is not possible in string theory. Okay. The laws are given once and for all. Okay. In particular, we cannot demand that nature looks the way it looks to us. Okay. For example, you are all familiar with the fact that the dimension of space in which we live is 3, right? We have up and down, okay, front and back, and left and right. Okay. This you cannot demand of string theory. Okay. You have to just take whatever string theory gives us. Okay. We cannot also demand that different vibrational states of the string behave like the elementary particles you observe in nature. String theory will give you some elementary particles and you have to live with those elementary particles. Here we encounter our first bottleneck. Okay. one finds that after detailed calculations, okay, this is not something that one can explain in a 1 hour talk. Okay. Then after some detailed mathematical calculations, one finds that the string theory, the dimension of space is not 3 that you are familiar with, but 9. Okay. Now 9 dimensions look very strange, right? How can we even think of 9 dimensions? And in fact, nobody can really visualize how a 9-dimensional space looks like. Okay. But you can describe it mathematically. Okay, a 3-dimensional space, to specify a point, you need 3 coordinates. Okay. Similarly, the 9-dimensional space, to specify a point, you need 9 coordinates. Okay, that's the way we should think of what a 9-dimensional space really means. But clearly, this is not what we see in nature. Right? We don't see 9 dimensions in nature. We see only 3. This was all that was there to the theory. Then we can just forget about string theory. Okay, we can say, okay, it gives a theory of gravity, but it gives a theory of gravity in 9 dimensions, which is not what we want. But this is not the end of the story. And the reason is that even though the theory is intrinsically 9-dimensional, it can actually be made to appear as a 3-dimensional theory by using some idea which is known as compactification. And what I'll do is I'll try to explain the idea of compactification. Okay, how can a 9-dimensional space look 3-dimensional? Okay, by considering an imaginary world which has only 2 dimensions. Okay, and the reason is that we cannot really visualize 9 dimensions, right? Because how can you see? I mean, I cannot draw 9 dimensions on this slide. Okay, but the essential mechanism will be the same. Okay, so let's imagine that you are living in a 2-dimensional world. Okay, that's not hard to imagine, right? You imagine that you are living in a flat land. You can walk this way or you can walk that way, but you cannot go vertically up and down. Okay. So such a world is a strange, but you can imagine, right? The flat land, maybe ants are a good approximation to such 2-dimensional world because they can only see move on a surface. Now let's imagine that this 2-dimensional world, okay, is not the one that we are imagining, infinite in both directions. Okay, but that this 2-dimensional world is the surface of a cylinder. Okay. Now here we forget about the interior of the cylinder. Okay, you only focus on the surface. Okay, and if you have a cylinder, the surface is 2-dimensional. Okay, and imagine that there are creatures living on this surface. Right? How will the world look to them? If R is very, very large, okay, then the world will look like the standard 2-dimensional world that you are familiar with. Right? In particular, if R is larger than the most powerful telescopes that they may have, okay, they may not even know that if you go say 2 pi distance in one direction, you will come back to our original point. Right? Because the only way to see that there is this finite size in this direction is that you have to either walk yourself or you have to send a ray of light which will come back to you after traveling this distance. Okay. But because light travels at a finite speed, if R is sufficiently large, then by the time the light comes back to you, you may be long gone. Okay, so from your perspective, it's no different from a world that is infinite in both directions. We could also consider the opposite situation, where R is very, very small. Okay. Imagine that R is smaller than the resolution of the most powerful microscope that you may have. In that case, this world will start appearing more and more as a 1-dimensional world. So in particular, if R is smaller than the resolution of the most powerful microscope, which as I told you today, we can only probe distances of the order of 10 to the minus 17 centimeter. Okay. Imagine that R was 10 to the minus 19 centimeter. Okay. There is no way you would have seen it today. Okay, because you can only probe distances up to order of 10 to the minus 17 centimeter. Okay. So in that case, this world will look no different from a 1-dimensional world. And it turns out that exactly the same idea works in making a 9-dimensional space look 3-dimensional. Okay. We simply take 6 of the 9 space directions to be small, okay, describing some compact space K. Okay. And when the size of this compact space is sufficiently small, smaller than 10 to the minus 17 centimeter, this space will appear to be 3-dimensional to people living in this world. Okay. So from our perspective, we will see only 3 large dimensions, and we will be led to believe that we are actually living in a three-dimensional world. Turns out that unlike in the case of the simple case that I described, where only one dimension is made into a circle, okay, and their circle was the only choice. Okay. Once you have more dimensions, you have 6 dimensions which you can you want to make into a compact space. Okay. There are many choices. Okay. So there are many different spaces K that can be used for realizing this idea. Okay. And so what we see is that even though string theory is unique, there is a single string theory, the laws are fixed once and for all. Once you compactify, okay, then it may have many possible realizations. Okay. So here is a 9-dimensional string theory that is a unique set of laws. Okay. But starting from this and making the 6 directions compact with on different spaces K, we can arrive at many different 4-dimensional, sorry, this should be D equal to 3, many different 3-dimensional spaces. Okay. Now nothing special about 3. Okay. You could have made into a 6-dimensional space or 5-dimensional space. So depending on what kind of space K you choose, okay, if you choose K to be 6-dimensional, then you will get a 3-dimensional, large 3-dimensional space. If you take K to be say 4-dimensional, okay, then you will get a 5 big dimensions. Okay, only constant the total dimension has to add up to 9. So the string theory, even though the theory is unique, it has many different possibilities. Okay. And these different possibilities, okay, the best way to think of this is as different phases of the underlying string theory. And I'll explain the meaning of the phases in the following 2 slides. Okay. So phase here you should think of in the same sense as the different phases of matter. Okay. You are probably familiar with the fact that the water, for example, okay, is just one phase of H2O. Right, water in H2O can also exist in the steam phase or the ice phase, for example. Right, there are different phases of H2O. Okay. So this is the analogy, the single. So if you just consider the theory of H2O molecules, right, which means that you just describe what kind of forces H2O molecules exert on each other. That's the theory. Okay, but given that, okay, it has many manifestations. Okay, the water molecules can exist as water. They can exist as steam or they can exist as ice. Okay, these are the different phases. Okay, same law but different manifestations. Okay, it's in that sense that string theory has the same laws, a universal set of laws, but it has many manifestations. Okay, and these appear as different kinds of 3-dimensional spaces or other dimensional spaces. Okay. And just as the environment inside ice, water, and steam are very different. Right? If you are living, if you didn't have the knowledge of H2O molecules, right? But if you are just living in ice or if you are living in water, okay, your environment will look very different. Okay, living in water is very different from living in ice, even though the basic laws inside water and ice are identical. Right? The theory of H2O molecules. Similarly, these different phases of string theory that corresponds to different choice of this compact space K, the environment will look very different. Turns out that for some choices of K, this 3-dimensional environment is very similar to the nature that you observe. And what this means is that it has elementary particles and forces similar to what you observe in nature. And this is what gives us further hope that string theory is not only a theory of gravity, but it is a theory of everything that we see in nature. Okay, that it can in principle try to get exactly the kind of elementary particles and forces that we see in nature. So one feature of string theory is that you have to get either everything right or you have to just throw away the theory, because as I said, in string theory it is not possible to tweak the laws. Okay. Laws are given once and for all. Okay. And so if from those laws you have to get not only gravity but also all the elementary particles, the forces that they exert and so on. You cannot just add some extra elementary particles into string theory and say that now you have a good theory. But the main challenge is to find a phase of string theory that has exactly the elementary particles you observe, and that's an open problem. Okay, and what I mean by saying that you have to get exactly the elementary particles you observe, okay, we demand, for example, that you have to get a particle like electron. Okay, it's not enough to say that the electron has properties, that particle has properties similar to that of an electron. The mass of that particle should match exactly the mass of the electron that you observe. The charge of that particle should match exactly the charge of the electron that you observe, and so on. So this is still a challenging problem. And one of the main challenges is to find possible phases of the system, right? And we have explored only a very tiny fraction of all the phases that string theory might have. Here is another analogy. Okay, imagine that you have a bicycle, and the bicycle moves following certain laws. But within these laws, there are many possible motions of a bicycle, right? You can ride it to the school, or to the market, or to the playground, or you may just decide to stay at one place, right? All these possibilities are realized by a bicycle. So these we can think of as different solutions that are offered by the laws of motion of the bicycle. But of course, not everything is possible, right? For example, you cannot use a bicycle to fly, or you cannot use it to move on water. So similarly, in string theory, there are many possibilities. The question is whether the standard model that you want, the standard model plus gravity, right? That what you know is what describes us. Whether it's like the different possible motions of the bicycle that are allowed, or whether it's like something like this that it can never be obtained from the laws of string theory. So this is the analysis. So similarly, string theory has some definite laws, but there are many solutions describing different phases of the theory. And the collection of all these phases is what has come to be known as the string landscape. That each point on this curve is like one possible phase of the theory. Many of these points are not like what we see in nature, so you can easily throw them out. And the goal is to find a point on this landscape which describes the nature that we see. And one of the main problems is that we have only explored a very small part of the landscape. It's still a big compared to what we are capable of, but nevertheless, it's very small compared to what we need. So the main problem of connecting string theory to nature then can be summarized in this two words, that you have to find our place in the landscape, right? We know we have explored part of the landscape, but you have to explore much more and see if any point on the landscape actually describes what we need, right? Which has not only gravity but also the kind of elementary particles that we see in nature. And then we may ask a more philosophical question: why are you there, right? If all of these are possible solutions in string theory, then why is it that one particular point in this landscape describes what we see in nature? Okay, we could have been anywhere else. So there is a possible answer to the second question, and that may be that no single phase of string theory is special, and it may simply be that the universe is very big and different parts of the universe exist in different phases, right? That some place maybe exist in phase 1, another place maybe exist in phase 2, and so on. And from this perspective, we see a particular phase of string theory because we happen to live in a particular region. This notion is what is called the multiverse. Okay, that it's as if our universe is consisted of many mini universes. Well, each of the mini universes is as big as our observable universe, universe that you have observed, of course. And in some part there is phase 2, some part phase 3, and so on. And we happen to be in some part where the phase of the string theory that is there is what we see today. So this is what we can call the main stories, and this is more or less the end of the main part of the talk. Like the great epics, string theory also has many side stories. And these side stories involve possible application of string theory to solve problems in related fields. For example, black holes are objects in gravity, in fact classical gravity. And there are many puzzles involving black holes which are independent of string theory. However, string theory, because it's a theory of quantum gravity, it has been able to address many of these issues that arose in the study of black holes prior to string theory or independently of string theory. String theory has also been used to solve problems in what is called quantum field theory, These are the theory of point particles. Okay. And finally, string theory has had many applications to mathematics. Okay. Because string theory is a consistent mathematical framework. Okay. Nevertheless, its consistency is not automatic. Okay. Often what happens is that in string theory, the same answer to same question, you can calculate in more than one way. Okay. And then the question will be, do they agree? Okay. If the answer to the same question turns out to be different by different ways of calculating it, then clearly the theory is inconsistent. Okay. And often one finds answers which look like they are not the same. Okay. Nevertheless, if string theory has to be consistent, they must be the same. And later on, mathematicians went ahead and actually proved that those two expressions that don't look the same are actually the same. Okay, so this way string theory has led to many new identities that in mathematics that mathematicians didn't know of, but they discovered it because of the internal consistency of the theory. So all these clearly make string theory a rich subject to study and explore. So let me now conclude by giving the summary. Okay. So what we have tried to say is that string theory is an attempt to formulate a theory of elementary constituents of matter. It's based on the idea that different elementary particles are different vibrational states of a string. I've also told you that string theory provides us with a consistent quantum theory of gravity and possibly of other forces. Main challenge, however, still remains, and that is to find a phase of this unified string theory that describes the world around us, and that remains a challenging problem for the future. Thank you.
मुझे लगता है इतने कमाल के इंस्पायरिंग थॉट प्रोवोकिंग टॉक के बाद इतनी कम गड़गड़ाहट की तालियां शायद इस यूनिवर्स के 3 डायमेंशनल स्पेस में कम पड़ जाएंगी. लेट अस गिव वन मोर टाइम बिग राउंड ऑफ अप्लॉज बिकॉज जो आप देख रहे हैं, सुन रहे हैं, या हम जो तालियां बजा रहे हैं, ये हमारे ऑर्डिनरी 3 डायमेंशनल यूनिवर्स की बातें हैं, और वी आर टॉकिंग ऑन बियॉन्ड 3 डायमेंशंस आल्सो. सो नाउ वी विल ओपन दिस फोरम फॉर क्वेश्चन एंड आंसर, एंड देन विल कंक्लूड. अगर आपके सवाल हैं तो आप पूछ सकते हैं. और सबसे बहुत बड़ी बात हम ये कहना चाहेंगे कि इस लेक्चर के लिए इतना ओवरवेलमिंग रिस्पांस रहा है स्कूल एंड कॉलेजेस की तरफ से, तो पैरेलल लाइव स्ट्रीमिंग भी हम कर रहे हैं. हमारे ऊपर एग्जीबिशन हॉल में भी पूरा भर चुका है, और उसके बाद एक सेकंड जगह और हमने ऑर्गेनाइज की है, वहां भी बच्चे बैठे हैं. सो हूएवर इज वाचिंग, प्लीज डोंट वरी. सर हम जब ऊपर आएंगे तो फ्यू मिनट सर आपसे मिल जरूर लेंगे, ताकि आप लोगों को ये लगना चाहिए कि आप सर के टॉक अटेंड करके गए हैं. विल डेफिनेटली गिव यू एन अपॉर्चुनिटी. कोई सवाल है? लगता है दैट्स वेरी इंटरेस्टिंग कि आप स्टिल यू हैव बिग होप टू conceive questions on that very matter. On that note, we'll conclude here, and before that, online questions. Yes, बोलिए. मुझे दिखा. Okay, so on our live streaming, we have a question from Vichar Sivhare. As photon is closed string mentioned in boson string theory, then letter took as open string. I want to ask that can we took photon close to string as a bound state of two open string? Don't know. I can't.
Okay, at least in the way we understand string theory today, even though as I said we have not gotten the standard model out of string theory, the photon is not a bound state of two open strings. It's really one open string or one closed string. Okay, so the idea that each elementary particle corresponds to a particular single string. Okay, and they just look different. Photon looks different from electron simply because photon corresponds to one vibrational mode of the string, electron corresponds to a different vibrational mode of the string. Okay, but this again may change in future because we still don't know how the standard model emerges out of string theory. Okay, it's only after we know the final story that we will be able to tell what exactly the photon is in string theory.
आई थिंक आप लोग कंफर्टेबली किसी भी क्वेश्चन को अगर हिंदी में भी पूछना चाहते हैं तो पूछिए. वी हैव डॉक्टर अनुरुद्रा फ्रॉम आइसर. आई कॉल हिम ऑन स्टेज सो दैट ही कैन आल्सो ट्रांसलेट. अगर कोई मन में कोई भी सवाल हो, नॉट स्ट्रिंग थ्योरी, सर इज वेरी मच ग्लोबली नोन फॉर थियोरेटिकल फिजिक्स. कोई सवाल फिजिक्स में हो, मैम का एक सवाल ले लेते हैं. Yeah.
Understand poetry. Yeah, maybe. I see.
Sir, I think we'll conclude here. And before that, I have one question on behalf of all of them. I think they are not asking. They must have enjoyed this talk. String theory offers a consistent quantum description of gravity at experimental verifications remains out of reach. In your view, what kind of conceptual and technological breakthrough rather than just higher energies might eventually allow us to test or falsify such theories? What is your take on that, sir?
Yeah. So I think the point, if we can understand how string theory makes connection to nature, for example, when you try to get the standard model, okay, if we can get there, okay, then string theory will tell you not only that there are particles like electrons, but it will be able to make a precise prediction of the electron mass, okay, or the mass of the muon, all the elementary particles, and it in principle should be able to make it more precise than what has been experimentally measured. Okay. And then the experimental measurements can be improved and try to test those predictions. Right? So once we can make a connection between string theory and what we really see today, okay, then there will be a lot of predictions. Okay? But that can only be done after we understand how string theory gets connected to nature. Besides that, if you want a more general prediction that we can see without actually defining how the connection works, okay, there you have to go to high energy, something which is model independent, right? Which doesn't depend on what compact space you choose or what kind of phases we have. The clear prediction is that if we can probe distances of the order of 10 to the minus 33 centimeter, okay, you will definitely see the string structure. Okay? It's just that getting there is hard.
Oh, thank you. That means we need to wait for more advanced subatomic world technology so that we can go further deeper. Thank you on that note, and I'll call Dr. Anuruddha from ISA Bhopal. He's a part of it, and request him for concluding remarks. Thank you.
Okay, so before I conclude, I thought I'll ask one question on behalf of you to Professor Sen. I think all of you are school students. So I'll ask him what would be college BA. So what would be your suggestion to people of 8, 9, 10, how they should prepare themselves if they're looking forward to a career in science?
I would say that you have to basically study well, try to understand things that you are reading, right? Not just memorize, but really understand what you are studying. Right? That's the most important point at this stage. Right? The if you can distinguish between what you understand and what you don't, okay, that is a very big step. Right? You should be able to have a clear idea in your mind that these are the things I understand and these are the things I don't understand. Because in that case, you can try to understand what you don't understand. Right? So one shouldn't get the false impression of understanding something, right, and going ahead. Okay? And that I'll say is the most important thing. Other than that, you just focus on your studies. You see if science interests you. It's not necessary that everybody has to go into science. Okay, it depends on your interest. But if science does interest you, you try to study things at a deeper level.
Sir, sorry to trouble you. One last question very
Yes.
quickly, because we are in Science Center. This is National NCSM's one of the science centers in Bhopal, Madhya Pradesh. सबको जो भी स्कूल में है, कॉलेजेस में है, या इवन जनरल पब्लिक, आपकी नजर से सर साइंस सेंटर विजिट करना क्यों जरूरी है, या आपको क्या लगता है सर? मैसेज फॉर दैट.
I think it's important because you get to learn things that are not part of your curriculum, right? And that's more important. That it's not that you will understand everything, right? In fact, most of the time you will probably not understand anything. Okay? But just the fact that science exists, that some subject exists that where work is going on. That itself is a knowledge that will stay with you, right? So I think it's important for that reason, right? The outreach, in fact, I mean, it's also from our point of view, outreach is important, where it's necessary to convey to people what we are doing, even though communication is hard. Many people may not understand what we are saying, right? But some dialogue is certainly important, and science centers can play an important role in that. Okay. I'd also say that, I mean, if you are interested in maths, there is something called Math Circle, okay, which is there in many cities, but there is also an online version, and you can easily join. I think they meet once a week or so, and then you are basically given some math problem to solve. Okay, and you just solve it. You interact with people who are supervising and so on. I think Arnab can tell you probably more about the Math Circle.
So, my name is Arnab, as Saket said, and I am in ISAR Bhopal. But before that, one of the thing is also I am a Professor Sen student. I roughly met you when I met him when I was in college, and he has played a very influential role in my life. I'm telling this because I'm also from a small town, smaller than Bhopal. We happen to had a science center, and science center influenced me at a earlier age to pursue a career in science. And later I pursued my interest, and now I am here at ISAR Bhopal as an assistant professor. So I will, if I can do it, I'm sure most of you can do it. So if you think you want to do science, you should really pursue that, or whatever you want to do, you should pursue a passion. Okay. So Saket has okay. Another thing Professor Sen mentioned about the Math Circle of India. So in ISAR Bhopal, we have a local chapter. So if you are interested, you can get in touch with the Math Circle of India Bhopal chapter, and we'll be very happy to have you in our campus. Okay. With that, let me conclude this. So I hope this talk has inspired you to ask deeper questions about nature, and that I'm sure many of you will choose uh, to pursue those questions, and hope probably will choose a career of research. Um, ISAR Bhopal, as you know, ISAR Bhopal offers a strong platform for motivated students to begin their journey towards understanding nature. In particular, Professor Sen spoke about string theory, and ISAR Bhopal also has a very vibrant research group working in string theory. So we all invite you to our campus, come and interact with us. This lecture is part of the 20th Asian Winter School. So this Asian Winter School is a pan-Asian collaboration between between China, Japan, Korea, and India. It happens to India once in 4 years, and first time happening in ISAR Bhopal campus. We're very happy to have that. We're very thankful to our institute and the Murthy Trust, especially for the Murthy Trust to fund this event. Um, with that, I thank once again Saket, his team, and the Regional Science Center to make this event possible so that we can talk to you in this platform. We hope to see you again in our campus. Thank you, Saket. No, so now I will request Saket to give a small memento to professors. On all of us. Huh?